Welcome to Study Loop.
So in this problem, we have two parts. In the first part, we are given 350 milliliter buffer solution of certain concentrations of HF and NaF, and we need to find out the mass of sodium hydroxide, which this buffer can neutralize before the pH rises above 4. So to do that, let's first write down the informations we are given here. So we are given the acid and base concentration. Our acid concentration here is, or the concentration of HF is 0.150, and also our base concentration or NaF concentration is also 0.150. Now, since as we know that if in a buffer, uh, if the concentration of acid and base are same, in that case we will have the pH of the solution or the buffer equal to the pKa of the acid. So here the Ka value of the acid is, Ka value of this acid is 3.5 times 10 to the power minus 4. That is the Ka of HF, and if we take the negative log of this value, we'll get the pKa as 3.45. So since the concentration of the acid and base are same, this is also our initial pH of this buffer. Now we need to find out um, the mass of sodium hydroxide which can be added and which will be neutralized by this buffer system before this pH raises beyond 4. So to do that, let's first find the initial number of moles of the acid and base we have here, and then we will set up an equation that will occur due to the addition of this sodium hydroxide here. So our number of moles of HF here is, as you know, that the number of moles is basically the concentration times the volume of the solution or buffer, and the volume here is 350 milliliter, and if we convert it to liter, we'll have 0.350 liter, and by multiplying these two, we will have a number of moles of 0.0525 mole. And since we have the same concentration of base, so our number of moles of the base will also be 0.0525 mole. Now we set up the equation that will occur when the sodium hydroxide will be added. So the added sodium hydroxide will react with our the acid or HF here, or basically our OH minus ion of the sodium hydroxide will react. So we can just write that part, and this is an aqueous, HF is also aqueous, and in the product we will get F minus ion as aqueous, and OH minus and H plus will form H2O, which is a liquid. So Now, so before the addition of this hydroxide ion or the sodium hydroxide, we had this number of moles for the acid and base. So our number of moles of acid was 0.0525, and our number of moles of base was also 0.0525. Now we have added, um, so we have to find out um, the amount of base we are adding here to fulfill the requirement or the condition. So if we consider that we are adding x mole of this base, then our after the addition of this sodium hydroxide, our number of moles of acid will be 0.0525 minus x before because this amount of base will react with the same amount of acid. So in the resultant solution, we need to subtract um, this amount of moles or this amount from the acid. And then in the base, or since the base in the product side, we are actually adding the same amount to the base. So reacting or introducing x moles of sodium hydroxide to the solution means it will um, reduce x mole of acid and will add to the x mole of base. Now these are our new number of moles. Now we have to plug these values in our Henderson-Hasselbalch equation to see what is the value of x, and from the value of x we will be able to calculate the mass of the sodium hydroxide we are adding here. So in the Henderson-Hasselbalch equation, we know the pH is equal to pKa plus log of or here we can just write the moles of base over moles of acid. Now so the pH, that is our limit which we cannot exceed here, is 4. So our pH value is 4, and the pK value we already calculated as 3.45. And now we just put the moles of base, which is 0.0525 plus x, and moles of acid, which is 0.0525 minus x. And if we just solve this equation for the x here, we will find a value of x as 0.03. So that is the number of moles of sodium hydroxide we are adding here. So from the number of moles of sodium hydroxide, we can easily find the mass of sodium hydroxide we are adding here. So as we know that the number of moles is equal to mass by molar mass. So if we just time it by the molar mass of sodium hydroxide, which is 39.996 gram per mole, and then we will get the mass of sodium hydroxide we need to add here, and the value is 1.2 gram. So this is the mass of sodium hydroxide that this buffer can neutralize before the pH rises above 4. Now in the second part of the problem, we are given exactly same requirements or criteria. Just in this case, the concentration on the buffer, the concentration of the acid and base was 0.350 m for both the base and acid instead of 0.150 m, which we just dealt with. So for this second part, what we need to do is to simply um, again we just find the number of moles of the acid and base for this case. So in this case, our concentration of the acid is 0.350, and the volume of the solution is also 0.350 liter. So our moles of acid will be just the multiplication of these two, and our value will be 0.1225 mole. So that is the moles of acid. And similarly, since we have same concentration of base, so our moles of base will be also 0.1225 mole. Now, as before, if we just go back to our previous equation, so similarly we will here add x mole of base, but in this case we will have only these values replaced with 0.1225. So that means that in the final solution we will have to just subtract x from here and add x to here. So if we just set up the Henderson-Hasselbalch equation for this case, in this case our pH is as before so our pH limit for this case also is 4, and our pKa value is as before, it is 3.45 plus log over, in this case our resultant base concentration is 0.1225 plus x, and our resultant acid concentration is 0.1225 minus x. And again, solving this equation, we will have the value of x as 0.068 mole. So this is our mole of sodium hydroxide for the second case, where our acid and base concentration is 0.350 molar. So if we just multiply this number of moles by the molar mass of sodium hydroxide, we will get the mass of sodium hydroxide here. So we multiply it by 39.996 gram per mole, and our resultant mass of the sodium hydroxide will be 2.7 gram. So this is the amount or the mass of sodium hydroxide that the buffer of 0.350 molar HF and 0.350 molar sodium fluoride can neutralize before the pH rises above 4.